So now we're doing screen recording. Okay, so the question is now, we have the relations, like we have the first one, the second one is Bob, for example, and then we have attend, so we have the lectures L, they have kind of other numbers, L1, L2, with one with databases, and one, for example, with software engineering. And then we have a third relation, attend, which actually contains who's attending what. Okay. So the idea is, if you have three relations and you as a programmer, how would you implement this query? Yeah.
You start from left side, first those selection, those join, then right side, the selection, and then.
So we would go to start with students, okay? And then?
And then join with attend.
Mm-hmm. How would you do the join?
Like how?
Hmm?
It means that it goes like one by one. What you mean by how it does?
How do you implement the join? So in any programming language, how would you do that?
Programming language with use for loop.
So nested loop. For loop would mean nested loop. Yeah, we can do that. So we would start. We have a big for loop here. So we would have a big for loop where we iterate our for and then s in students. And then we would say, okay, for every for in attend, a in attend, and then would say, okay, first where s dot number is equal to attend dot number. Okay, so this would be the first possibility of a join. Yeah. Yeah. So I think it's better to show you some examples of, so actually basically how does a database system work then. So the first thing I want to show you is like the volcano model. So if you have a database system like PostgreSQL, and the PostgreSQL basically implements the volcano model. And the idea is, okay, that every operator basically has two operations. So yeah, I'm kind of struggling where it's actually pushing tuples up clockwise, and yeah, it's the iteration. Open and next. Okay. So actually before the volcano model, here's kind of an idea using with sorting. So the idea is, okay, we want to still implement intersect, and the idea is, okay, we have left, right, and compare. And the idea is, okay, we have the left input, so assume the data is sorted, and then we can say, okay, give us a tuple from next from the right side. So now we would have two relations here, S and R, and you want to know, okay, 1, 1, 2, and here 2, 3, 3. Okay, and so the idea is, okay, this is already sorted, and then we would have a big pointer, so we have a big for loop, only one for loop, and this is actually the maximum. And then we would say, okay, while input is not exhausted, so we have one pointer, one pointing to the right side, one pointing to the left side. And this would be incremented every time, so we compare it, and then here, if it's smaller, then we would go, okay, we increment the left side here, the left side until the first tuple is equal. Okay, so this is the example shown here. If you would, so we would have the nested loop, we would have n squared complexity, and now the idea is we have two sorted lists, and then the idea is, okay, we only have one pointers, and we can just say, okay, get the next tuple from the left side, the next tuple from the right side. And basically the idea is, okay, we say we do not know about the next tuple. So the idea is, okay, assume we do not know anything, so we can only see one tuple at a time. So here we only see this tuple, and from the right side we see this tuple. So then we wouldn't have any pointers, we would just see one tuple. And then we would say, okay, we compare it, and if the left side is smaller, then we can say, okay, let's have a new tuple from left, get next. Okay? We would say, S, please get next. And then, if we have the next tuple, and we see it is still smaller, then we would say, okay, S, give us the next tuple. And then we can see, okay, it's the same, so we can increment both sides. And we would say to both relations, get next. Okay? And that's now the idea of set-oriented processing. We have two tables, and we ask for the next tuple. Okay? And this is actually what the volcano model is all about. So the idea is, okay, we have the volcano model. And this means that we have one big function, and this is called next. And every operator in between. So every selection, every join. Join, selection, or what else? So here, whatever it might be. And here we have an input relation R, and here we have an input relation S. And basically what we do now is, we ask, every operator asks the underlying one, get next. So the join has two sides, and also the intersect would have two sides. So this operator would do for both sides. Next, next. And so on. Okay? And that's actually how a database system processes data. So we would ask all the underlying one for the next one, and until, and actually next returns true or false. It returns true as long as there's a new tuple. And it returns false when there's no tuple anymore, and the tuple is stored somewhere else. And that's actually how it works. And so this would be the example for an intersect. So we would have, quite simply, we would have an intersect and two tables S and R. And here we would ask for next. So the output, if you want as parent operator, if you want to have a tuple, and then we would say, okay, T1, T2. So this is T1 next, and this is T2 next. Yeah, and we would do this until input is not exhausted. And basically that's all. So this is the most important thing. PostgreSQL, for example, or DuckDB, they're all implementing the volcano model, and that's how it works. Yeah, and so actually what we're going to do next is we're discussing all the different operators and how they actually work with next. Questions so far? If not the case, we can continue. So again, each operator produces a set. So we just see the set is actually every tuple. It's just the set of every tuple we have. and every operator consumes 0 or more input data sets, or more sets, so the table scan, so it's the bottom operator. This is the sync so actually that's the basic operator, so we have a table scan. The operator consumes 0 operator, so it would be a table scan, and then selection, and every unary operator consumes only one set, and joins, for example, consumes 2 sets. So table operator, table scan, 0 input, 1 input, 1 input, 2 inputs. Okay, we do not assume anything about the input, it's just an arbitrary number of sets, tuples, and therefore we can combine them flexibly. Okay, so actually I talked in the previous slide about the volcano model, and more easy, so actually basically we could also have full materialization. Full materialization means, as you would implement it in C++, you would have, okay, for every operator means we store the whole input and store afterwards the whole output. So this would be actually operator at a time full materialization. So this would be also called operator at a time. Because you process each operator as a whole. So for example, if you have a selection first and then a projection, you would first select the whole input data and store it somewhere else and materialize it before you can call the other operator. So you would process one operator at a time, and in between you would materialize the full output table. You have access to a full materialized input table, and you would have access to a fully materialized output table. So you process it, all the set as a whole, and do not forward one tuple to the next operator. So for example, if you're going to do GPU programming, so the default thing would be to have an operator at a time, one kernel, which processes one operator. And it has the downside that materialization is expensive. And if the data is larger than main memory, you have to swap the pages in and out, and this would be expensive. One possibility would be MongoDB, who's implementing this full materialization. Then, and actually that's what's implemented, is the iterator model. So again, that's what I implemented. I explained to you previously. The iterator model is also called the volcano model. Volcano. Oh no, the C is missing. Volcano model. And actually that's state of the art. So the idea is, okay, you have the next operator, and the next operator gives you access to the next operator, to the next tuple. And it has the advantage that the data is pipelined, so you can already head over the data, a tuple to the next operator. So we do not unnecessarily materialize data, and it has a flexible control flow. So for example, as long as there's no operator that breaks the pipeline, for whatever reasons, for example for a join, we can still forward the tuple and have the tuples processed flexibly. So we can also process it in parallel, as long as we can, one tuple is not interfering with another one. But as you said, you have the many next calls. So you have a next call for every tuple, for every operator. And that's the downside actually of the iterator model, because you have millions of virtual function calls. If you implement it, you have a base class operator, then you have an inherited class binary or unary operator, and then actually each concrete implementation, like the selection, the projection, and so on, inherited is a child class of this abstract class, and therefore you have millions of virtual function calls. Because you have the abstraction, like you have the interface with next, and therefore you have to find out what kind of actual implementation it is, and therefore you have millions of virtual function calls. So again, the basic operator you have is next, because with next, this gives you the next tuple, so repeated calls to next produces the output stream. And that's actually the most important thing about the iterator model or volcano model, the next call. You have as many next calls as tuple you have. Okay, you have also an open and close, so open starts the connection and close does some finishing work, but actually the most important thing is the next function, and the next function is called repetitively for every tuple, for every operator. Okay, so how to pass the data from one operator to the other, and two possibilities, like you have two tuple pointers, like you have the initial place where it is stored, and then you just pass the tuple pointers to the next, like you have the output of the next call is just true or false, true if there is another tuple, and then you have a certain place where actually the tuple pointer is located, and the next possibility is to pass the function pointer not at all. You have a global data space, the registers, and then you have subscripts to operate on these registers. So if you have certain offsets, this would be the subscript like in an array function. So an intermediate thing between full materialization and the volcano iterator model would be blockwise processing. And this is the idea, actually it's like the volcano model, but instead of one tuple you have a vector. And this is also called vectorized processing. Because like it would be implemented instead of having one tuple, so you say next, and normally you get one tuple, but instead you would have a full vector of tuples. But we're not going to discuss this in detail. And then at the university where I did my PhD, we have created another thing, and this is called the push-based processing, also called the producer-consumer model. So this is called producer-consumer model also. And the idea is, okay, so normally if you have the volcano model, like you would have the next call, so it would start at the top. Like you would say, okay, you have a join, and you have selection, or projection, and a table scan. And normally you would start from top to down. You would ask top, is there another tuple? And so on. Is there another tuple? And so on. And instead, we now say, okay, we push each tuple upwards. So we say, okay, instead, ask the parent operator doesn't ask the child operator anymore, but the other way around. The child operator says to the parent operator, here, I still have another operator, so please consume it. So we'll say, okay, please consume my data, consume it, and so on. So we would have inversing the tuple flow. Yeah. And this would be the push-based operator model, what's also called producer-consumer. Because you see, we have this consume function, therefore it's called consumer, and the other way around, before we start consuming, we have also this kind from top to down. We first start at the top and we are saying, okay, please child operator, please produce the data. So instead of the next operator, we would say, okay, please produce any data, and so on. And then this will be done before the child operator says, okay, I have produced my data, and now parent operator consume my data. And why are we doing that? Because like initially we have the millions of virtual function calls, and instead this would end up by, so we would have this big while loop. While next is not false. And then we have to ask next, 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 and so on. And the other way around, we would just have a big for loop. So every table scan would produce one big for loop. For S double punct S in S, and here for R in R. And we would only have two big for loops, and we would avoid any virtual function call. So that's the idea. I will show you the producer-consumer model. I will present it to you in more details later on. But before that, we are going into detail about the iterator model. Yeah. So now you have seen 4 different kinds of implementing an operator model in database system. So actually now you know everything about how a database system processes data. So these are the abstract concepts, and every time you're using a database system, one of these 4 models are used. Okay, so I have no questions so far. We can have some examples. Okay, so here we have 2 operators, actually 3 operators. We have the table scan, we have a selection, and we have the cross product. And we have, if we have fully materialized all the data, so what actually we do, if we have a table scan, okay, we would return the whole table. So full materialization would mean we return the whole table. So the selection would mean, okay, we first materialize the whole table that we got, and then if we want to do a selection on the whole data set, so as we know this is the operator at a time, we have to do the operation on every tuple here, and we have to materialize the resulting table here before we can proceed to the next operator. So this is operator at a time. So you see, we're returning the full table first, and then we do the same operation on the whole data set, and we materialize the data set before we can continue with another operation, of another operator. And here the cross product, as you have said before, would be just 2 for loops, and we would combine them, and we would return the whole table. So this is fully materialization, quite easy. And this is how it is implemented in MonetDB, for example. So now, the iterator model, also called the volcano model, and basically, like this is just the table scan. And the table scan, as I said, the most important function is next. And basically what next does is, okay, as soon as next is called, and there is a tuple. So internally we have the tuple identifier. And the tuple identifier that counts from 0 to the cardinality of the table. So the size of the number of tuples. And every time next is called, we increment this tuple pointer, and then we say, okay, we return true, and the tuple is located at a certain position. So that's how the iterator model works. Quite easy. So it's everything is about next. And so this was the table scan. So now let's discuss also the other operations, so the selection. So how does it work? Okay. So the selection has also a parent, and it says next, okay. And basically if the underlying, so actually what we do is we ask for every tuple we get from the underlying one, we check the predicate. So we here inside, that's actually the where predicate. So we have the where clause, and the where clause here is checked. And if we have one tuple from the underlying operator, for example the table scan, for which the predicate qualifies, then we return true. Otherwise, we ask the child operator for the next tuple because the last one did not qualify. So we asked the child operator for another one, and we do this until one tuple qualifies, or if there's no tuple, we return false. Quite easy. And last but not least, the cross product. The cross product has two sides, and we have to combine every side with the other side, and therefore we first have to ask the left side for another one. So where is it? So while true. So step on the left side, so step is true, and then as soon as there's no tuple from the left side anymore, we finish. Otherwise, if we have from the left side a tuple, we ask from the right side to return the next one. And we do this until either the left side or the right side doesn't have any tuple anymore. So basically here, we do it for the right side. And if here the right side doesn't have a tuple anymore, we jump into the outer loop, and then, so we have to process the right side totally. So again, we get the next tuple from the left side. So I can show you maybe an example. So we have two tables, S and R. So this is left and this is right. So what we do is, so we start here with left dot next, and then we have the other pointer on the right side, right dot next, then right dot next, right dot next, and then if this is not the case, we say step is true, and step means here step, this would be incremented, and then we do the whole thing again for the right side, and we do this until here the left side does not produce any results anymore. Yeah. So this would be the cross product for the iterator model. Okay, so blockwise processing, as I said, that this would be vectorized processing. So we also have the same interface like the volcano model, but instead we would have a number of tuples. So here, for example, we would process 1,000 tuples at a time. And don't get confused with vectorized processing at CPUs. So this is completely a different thing. So for example, CPUs can process more than one register at a time. So for example, with AVX 512, you can process up to 512 at a time. And this is totally a different thing. So if you're talking about blockwise processing or vectorized processing in database systems, that means that you are using a C++ vector, so just an array of, for example, in this case, 1,000 tuples. So here you can see, with next, we are returning 1,000 tuples at the same time. And then we have the same operation, for example, for the selection. So then we have to do the selection for every tuple within our current vector, and then we have to adjust the length. So here, so we have to, if not every tuple is qualifying, so for every tuple within our vector, we have to check the predicate, and then if we have more than one tuple that qualifies, we return the result vector. So and here the cross product. So then we have, for every tuple on the left side, we have also to do it for the right side. So here we get the tuples, and then actually for every tuple on the left side, we have to do it on the right side. Yeah, I don't want to discuss this in detail, so it's just for every vector on the left side, we have to connect it with the vector from the right side. So basically that's the idea. the way, if you're interested in really implementing that, I'm looking for students working with Dt-Db. And actually I started with implementing higher order lambda functions. So I've accepted a proposal on higher order lambda functions, and I wanted to use lambda functions. So Dt-Db actually what they allow, if you have an array data. So Dt-Db, so you have also in PostgreSQL, violating the first normal form, you cannot store a single value, but you can also store an array. So instead of having a single attribute of a single value, you can have arrays as attributes, where you can store more than one tuple, more than one value. And yeah, and like Dt-Db has lambda functions, which actually can be applied to these arrays. And I also want to use lambda function for other use cases. And actually, I succeeded in having an operator making use of this kind of lambda functions, but currently I implemented table scans, but I cannot deal with constants. I don't know why. And basically, I was challenged with blockwise processing because Dt-Db is doing that blockwise processing, and so I've started, but I did not succeed. So if anyone wants to finish, I would be looking forward to it. So actually it would be exactly this in C++. Okay, last but not least, produce a consumer model. And then, as I said, we have two functions. We have consume and produce. So basically, open would be consume. I don't know why it is not called consume. And how it works like, oh yeah, here you have consume. And how it works like, the parent asks the child, please produce code. And then the child one says, okay, here you have all my tuples. And basically it's a big for loop. And within the for loop it says, okay, consumer, please consume my code. And the idea is that you would end up like normal coding. Like if you would do it by hand, if you would do query processing by hand, you would also write a for loop where you modify where you access each single tuple. And that's actually the idea of the push-based model, that it would be like if you as a programmer would implement an operator tree, you would end up like this. So okay, the table scan actually starts the pipeline. For each tuple, consumer, please consume my tuple. And then, for example, the selection. So remember here, consumer, consume. So here, if the parent one is a selection here, it would say, okay, so please consume my tuple, and then the selection just adds this predicate. So it's just a single if evaluation. And if the tuple qualifies the predicate, then also the selection operator says, parent, please consume this tuple, and if the predicate if the tuple doesn't qualify the predicate, nothing at all is done. So the parent never knows about the tuple if it does not pass this predicate. And then last but not least, we have the cross product. And the cross product basically has two consume functions, because actually the cross product, so the cross product basically has two children, an R and an S, and basically it asks both to produce code. First, and then both sides tell him, okay, so please consume my code. So here we can see it. So we basically start with the left pipeline. So here left produce. So we would start with the left pipeline here. And then afterwards, consume from the left would be called. So this one would be called consume from left. And what happens here is the next produce would be called. So here the next produce would be called. And then, last but not least, consume from right would be called. So here we have an order. Like the order says, okay, we first ask the left pipeline to produce code. So then the left pipeline produces code and asks the parent to consume. Afterwards, the right pipeline is asked to produce code, and therefore the right pipeline produces code. So here this would be the execution order of these errors. Like first the left side and then the right side would be processed. And finally, we can do it for every tuple, and then for every tuple we tell the parent, so please consume our new tuple we have produced. Okay, so finally we can have a close function to release all the allocated resources, and like we would have some more things to do: rebind, memory management, and spooling intermediate results. For example, for joins, we mostly need intermediate results for joins. And for example, if we have a new operator, we have to rebind all the attributes. So if we want to have a map operator, would it be? So we would have an additional operator. We have to create a new attribute. I think this is called with rebind. So have a new operator, new attribute, edit. So this would be rebind. Okay. So the next question is about how to know where the tuple is located, and this is the idea of subscripts. And so we would have the attribute access, so it would be the attribute itself. So questions? So it's behind you. Questions? So here the subscripts, actually we have the attribute access, and we need that for predicates, to evaluate predicates, or to do the computations. And the idea is, okay, we need to know where the tuples are located, and therefore we have to implement them. And there are two possibilities, like having interpreting objects, and like here this is an example. So here we have the pointer, and then we just have the offset, so where it is located to the pointer. So the first attribute would be the first offset and so on, and this would be the pointer to the actual tuple. And this is one example, for example. And the other possibility would be a virtual machine, okay. And yeah, so actually I have not really prepared this slide. So here we have the operator where it is, and actually we have the operator pointing to a tuple, and then we have like the virtual function call here to the actual command, and then we could have, with this command, we could access the actual attribute. Never mind. And the third option would be in precompiled fragments. And the fourth option would be to generate machine code directly. Yeah. Okay, but what I have prepared well is pipelining. And the idea is, okay, you have an operator tree. And operator tree means you have the tuples and you push them upwards. So you have like the table scan, and then you push them upwards and so on until a join comes, and then you have kind of output, and then you have the other side and so on. And now the idea is, okay, every unary operator will be part of a pipeline, and as soon as we have two operators expecting two sets, we have another side of the pipeline. So here you see we have two pipelines, for example. And this is pipelining is good, because like that you do not have to materialize any tuple, you can just forward it. And there are some operators that need materialization. These are called pipeline breakers. And depending on the operator, if they can have subsequent results, they're a pipeline breaker, but if they do not have any subsequent results, they are fully materializing the pipeline, then they are called full pipeline breakers. Okay, and now it's up to you. What are pipeline breakers? What operators do you know? What do you think are pipeline breakers? So obviously there's one operator in this figure I've drawn, which is a pipeline breaker. So what is the pipeline breaker in this figure? Loud? The straight line? No. What is the operator? So the straight line is the pipeline itself. Like the green one is one pipeline and the red one is one pipeline. So what operator is the pipeline breaker?
The one where the two pipelines split up.
Yeah. How is this operator called?
Join.
Join, exactly. So first thing we understand is joins are breaking the pipeline. Why? Because for every join we have to first materialize the one side, because before we know whether there's a join partner or not. So joins are always breaking the pipeline. What else is breaking the pipeline? So in database systems, like all the clauses we have, select from where. What do we have else? What other clauses in SQL? Select from where. What are the others? Group by, order by, exactly. Having, yes. So and which of these clauses will be the reason for a pipeline break? Exactly, because group by, you have to materialize data. And therefore, you cannot forward each tuple at a time, because you have to wait for the others. Now this is a pipeline breaker, group by. And how is the operator called for group by? It's just aggregation. A group by means an aggregation. So group by aggregation is another pipeline breaker. And what was the other clause? The other clause you mentioned. Order by, exactly. Order by in a database system is a full pipeline breaker. Because for order by, it's like you have set-orient processing. You do not care about the ordering. So order by means a single is its own operator which does the ordering. So actually these are the most frequent pipeline breakers that occur. Order by, aggregation, group by, and every join is on one side a pipeline breaker. So you see on the other side it is not, but on the one side it's a pipeline breaker. Yeah, and actually that's it. You should know that within a pipeline we can forward every single tuple, but as soon as we have a pipeline breaker, we need to materialize one side. Is that clear to everyone? I guess so. Okay, what else do we have here? Some effects of different pipeline behavior. If a pipeline break is between source and sink, the original data is no longer accessible, of course, because we have to materialize it. So this is relevant for lazy attribute access if you have using the TID for join, for string representations, and so on. If a full pipeline break is between two operators, both are decoupled, the full pipeline break breaks the plan into fragments, can be executed independent from each other, relevant for scheduling. And of course, if you're generating code, we haven't discussed this, we must know about pipeline breaking behavior. And the next question is, how can we parallelize during query processing? So inter-query parallelism is simple, intra-query parallelism is much harder. So the idea is, okay, inter-query parallelism would be between, intra-query means one query at a time. So we can, of course, run multiple queries, but how can we parallelize one query? And independent parts of the query can be executed in parallel. So the idea is between two pipeline breakers we can work in parallel, and also within a pipeline we can parallelize. And the idea is normally partition the input. As we have a set, we can partition this set into multiple smaller sets, and this actually will be done for parallelization. Okay, so you know everything about the different models. Now it's time to discuss the different operators we have and how they are implemented. So basically now it's just we have focused on 3 operators: table scan, cross product, and selection. And now we want to focus on more than 3 operators. So that's what's about the next slides. So now you know how to implement 3 operators, and in the next slides you want to know how to implement more than 3 operators. So basically, again, we have relational algebra, and relational algebra has more operators than cross product and selection, and therefore we need to implement more than 3 operators. And as I said, pipelining operators are simple. Every operator which is part of the pipeline, for example, selection is simple, and as soon as there's an operator breaking the pipeline, it's complex. So joins are complex, aggregations are complex, order bias complex, and all the other operators. Projection, selection is easy. So that's it. And so the table scan is like the sync operator. So it's the basic operator, and it produces all the tuples within a relation. And by the way, this what we're focusing now. So on this slide, everything follows the push-based execution model. So all the operators that are presented here are implemented according to the push-based, so producer-consumer model now. So here you can see, okay, basically what we have seen previously, we have here a big for loop, and the for loop asks the parent one, so the consumer, to consume the tuple we have. And basically that's it. So what happens if we have more than one page? Then we have to, so if it's materialized somewhere on hard disk, then we have to access each page, and for each page we have to access every tuple. So table operator, as we have seen previously in the previous slides, according to the push-based execution model. Okay, so actually the selection is part of the pipeline, and therefore it's one of the most, it's very easy operator. So you just have to check the condition. If the predicate holds, the tuple is passed forward, and if not, nothing happens. And therefore it's quite easy. Another operator is map. And map actually doesn't exist in relational algebra, because map actually adds a new column. And so normally if you would have relational algebra, you could use a projection for that, but actually it's our own operator, and it's just having a new column, and therefore you have the tuple how it was, and then you have added a new column according to a function. That's it. It's also part of the pipeline. Okay, and now let's have joins. Joins are great. And joins are, of course, breaking the pipeline. And like what kind of joins do we have? Like if one side depends on the other side, like some nested queries. We have to evaluate for every tuple we have to check the other side. So two for loops, and two for loops would be called nested loop. So this has the worst complexity. So the idea is that the database system should avoid any nested loop join. So never use nested loop join, otherwise you need it. So, except you need it. So never use nested loop. So that's a rule for database systems. So the only thing that is worse than a nested loop join is a cross product, but actually it's a cross product. So nested loop is the worst thing you have. And therefore, the best thing is always the equi-join. So if you just check for equality, sorry, if you just check for equality, you can choose an equi-join. So in between, if you have greater or less, then you can also use a sort merge join. So this actually is missing here. So in between a nested loop join, there exists the sort merge join. So this is actually missing. You have also the sort merge join, and this can be used for comparisons, so smaller or greater. So smaller or greater. Question?
Is this same like the theta join?
Theta join means just the equality. I think it is, yes.
No, because in theta join we are comparing also.
Sorry, the join?
In theta join we are comparing also the columns. As you said, there was the sort merge join, so is the same as the sort merge join or they are different?
So the question is whether the sort merge join is the same like the theta join. So I think that. Sorry, I have to look it up. Sorry. So theta join is just. No, theta join is any arbitrary comparison. So it does not say anything about it. So theta join, so like, actually this is a theta join. So like you have the theta join is actually, so like if you have the same attribute, like if you have E1, so if you have the first table which has a join column n, and you have a second table E2, the join column and another tuple, and then if you would say, okay, you have E1 join E2. If you do not write anything there, then it would be a natural join. And otherwise, if you have here any condition, then it would be a theta join. So here actually every join gets, so actually this is a theta join. It doesn't say anything about equality. So theta join just means we are checking for a predicate. This is theta. Theta is the predicate. So in this case, it's just P. Okay, so sort merge join means we are sorting the table beforehand, and then we can compare for equality, or greater and less. And the best idea we want to have is the equi-join. Equi-joins are nice because then we can use a hash table. Okay, so basically nested loop, sort merge join, and hash join. These are actually the implementations, and hash join can be used for an equi-join, and for any other join you either need sort merge join or nested loop. Okay, so nested loop is the most flexible because it's like, okay, first you have to produce the right, you have to get for every tuple on the left side, you have to check for the right side. So here consume from left, and then for every tuple from the left side you have to look it up at the right side, and then if it matches the predicate, you can say the parent consume. Blockwise nested loop, so it's the same, but we have some buffers in between, so we can process more than one tuple. And yeah, so here we can materialize some in between, but I don't want to talk about the blockwise nested loop. And now let's talk about the third merged join. So we can assume each sides are sorted, and then, so we have only n log n complexity, but then we can have a pointer on the left side and a pointer on the right side. And yeah, it's simple in the iterator model, but not in the push model. So basically how it is shown here, it's actually more complicated. So we have both sides produce, and then we need to materialize what we have produced, and then we have to check it. Yeah. So basically we have two pointers, and we have to advance it on, so we check it always, and the smaller side has to increment it, and so on. And that's actually the sort merged join. And last but not least, best implementation is actually the hash join. And the hash join basically means we hash each value by the key. Like a hash map is just access by the key. Like here you can see it. We have to first, like we have the tables, we have a big table, for example, the left side. And the left side has a key and a value. And so on. Now the idea is, okay, this is stored like that. So we have a big hash table, and if we insert hash table from 1, we got this result. So basically what we do is we store t, so it would be a tuple like 1.a, and it would be stored inside of the hash table. And we would do this for every tuple here, and then if we have another table, R for example, and for every tuple we say, okay, for each tuple, for example, 1b, we say, okay, is there the key 1 already contained? If so, then we return this tuple, and then we can concatenate, and we can output this, we can emit this tuple. And this is actually a hash join. So we have one hash table, and you first materialize the one side, and then for every tuple coming from the right side, you have a lookup in the hash table, and you can forward the tuple like it is. Questions on the hash join? So I don't think so. Questions in the last row, the second most last row? Questions on the hash join? No. Oh, yeah, so basically that's it. So there are now some other kind of implementations, but actually I only want to briefly discuss them. So if the main memory does not fit, so the idea is, okay, you need a temporary segment, and then you have to partition into boundaries, yeah, but never mind, we're not going to focus on that. And this is actually if the implementation, if the hash join doesn't fit into memory, and then you have to repartition the left side if the partition is larger than memory, and so on. But actually I don't want to discuss about the so I am happy if you know about the difference between sort merge join, hash join, and nested loop. So that's everything you should know. So all the other things about the external hash join, it's not important, and actually I don't want to discuss with you external hash join. Okay, there are some other kind of join. That's a singleton join, and singleton join means there's only one join partner for every group, and so this is relatively common for group by and so on. And then it's easier because you don't have to consider the case there's more than one join partner, and this basically it's a singleton lookup. So for every side on the left side, you can just have one tuple on the right side. So it's another extremer. And then there's also some kind of other joins, like you have outer joins where you have to produce non-matching tuples also, so even if there's no joint partner, you have to produce the results, and there are semi-joints where you do not consider the other tuples, and there are anti-joints. But actually the implementation is the same. Like the implementation we have seen is the same. For example, if you're going back here to the hash join, where's the hash join? So here, for example, we only would emit a tuple if the predicate holds, and if we would have, instead of a hash join, we would implement an outer join, we have to emit a tuple anyway, even if there's no join partner found. So actually all the joins we have, they are working the same way. For the semi-join, you do not have to consider the other tuples, so it's easier, you do not have to materialize all the tuples, you can just mark matching partners, so you have less work to do, and anti-joins works the same, but instead you have to look for non-fitting partners. So all the joins are quite easy, similar. Yeah, non-inner joins mark tuples, as I said. For outer joins, you need an additional pass to produce tuples without a joint partner. Should be added with null values. Semi-joins produce only if not marked yet, and anti-joins is like the opposite, produce only non-marked tuples. And now the question is where to store the marker bits, and marking the left side is simple. Just on the left tuples for potential joint partners, and we need just 1 bit for every tuple, and then we can have, so we have all the tuples materialized, and then if we are having processing the other side, we're just setting a bit instead of emitting all the tuples themselves. Marking the right side is more problematic because we have to materialize also the other side, and we need kind of a data structure for that. Okay, but as I said, I'm happy if you understand the difference between sort merge join, hash join, and nested loop join. So that's all you need to know. Okay, so as I said, another operator that is breaking the pipeline is the sort, and like we cannot parallelize the sort because we want to force the output to be sorted. So sort operator is not the operator according to Ted-Cod interrelation model, because like it interferes set-wise processing because we want the output to be sorted. And like the idea, we only have one possibility. We have to load all the chunks, we have to sort, and we have to kind of, if it's larger than memory, we have to merge sorted runs, and yeah, so it only works by, okay, we have to consume all the tuples, we have to materialize the tuples, and then once we have sorted it, we have to emit it. So actually sort is one of the worst operators regarding performance, because you have to materialize everything and you have to sort it out. So the easiest possibility is in memory sort using quicksort, write it all out, and we can also have some other kind of sort, so it's like this basic sort operations as you have learned in algorithm and data structures. Yeah, and if you're using a sort merge join, you have to use merging algorithm and so on. Okay, so the next operator that is breaking the pipeline is the group by, and there are two possibilities. So the one is sort based and the other one is hash based. So one possibility is, okay, you sort it by a key, and the advantage of that is like it's not fully it's not a full pipeline breaker thing, because like if you're doing the sorting before, you can say, okay, as soon as you have, if the key changes like 1, so if you have 1, 1, 1, 2, 2, 2, so like if you have the input, if that's the key, and that's the value, whatever it might be, so you can iterate until you found where the key changes, and then you can already emit the first aggregate, for example the sum and so on. So you can do it using sorting, but then you have a complexity of n log n. The advantage is that you can emit tuple, also you have to process the whole data set, because you know the input is sorted. And the other possibility would be hash-based, but then you have to materialize, then it's a full pipeline breaker, but normally it's faster. So you have to aggregate the whole data, and then you have to put it into a hash table, and as soon as you have processed all the data, you can start a new pipeline. So here we can see, okay, we first have to consume it, and basically we have to enter the new entry within the hash table. So update the group using the function, for example. So like the hash table is always a key and a value. And for example, if the function is sum and we have a new tuple, and for example, if we have a new tuple coming in 1 and 1, key value, and then we want to update it. So we find the key here, and then we have to add this plus 1, and the new value would be 3. So this would be update. And otherwise, if the entry is not contained, for example 2 and 2, then we have to create a new entry. And if we have processed the whole data, we can just emit the hash table we have created. Okay, we first emit the first tuple and then we emit the second tuple. And that's it. That's how group by works. Another operator which is missing are the set operations. And basically all the set operations we have union, we have intersect, and we have except. And like the first is union all. Union all is the most trivial one, because like union all does not take care about duplications. So it's just okay, if we have two sets, we can just emit every tuple we have. Like two sides, we can just produce the one side then the other side. So this is one of the most simplest operators that exist. Union has to take care about duplicates, so we have to create a hash table to assure that there's no duplicates. So if there's a duplicate is found, we shouldn't emit it. Intersect is somehow similar to a semi-join. So instead of intersect, we can just process a semi-join. And with intersect all, we have to count it. So we have to count the groups inside of a hash table, and we only have to emit those which appear the same times. Except is similar to an anti-join. And again, for except all, we have to count the number of occurrences. Okay, that's it. So these are all the operators. Questions? So I'm happy if you know the difference about selection, join, so sort merge join, hash join, nested loop join, and order by and group by. So aggregation is important, join is important, yeah. And that's what I want you to know. And maybe I think in the next tutorial I have some examples to let you implement some single operators. Questions? If it's not the case, let's make a break. 50 minutes. So 5:45 we meet again.